All right. Hello, everyone. Let's start from where we concluded on the last class. So in the last class, we learned how revocation protocol works, and I introduced you to two representative revocation protocols, which is CRL and OCSP, and also the OCSP protocol's two other extensions called OCSP staple and OCSP most stable. So the and also I introduced a piece of research work that tackles into if OCSP most stable is actually ready for the web. Okay, excuse me. So the conclusion was the OCSP most stable was not ready yet, right? Because so there are three major players for OCSP most stable to be widely used reliably. So the first one is OCSP responders, which are managed by VAs. So they have to be really, fully reliable because whenever the web server needs to fetch OCSP response in advance, they have to be there, right? So, but we show that sometimes OCSP responders experience some outages. So OCSP responders are not fully reliable. And another one is web server software. So web server software needs to fetch OCSP response in advance, right? So what I meant by in advance is, let's say the web server did not fetch OCSP response in advance. And if it starts to fetch OCSP responses from the OCSP responder, when it receives a connection request from the client, then it is already late, right? Which means it has to hold the connections of the HTTPS connections, and it gets the OCSP response from the CA's responders and started to serve this response back to the client, then it is too late, right? Because the whole point of most stable is to return the certificate as well as OCSP response in advance so that the client does not need to send OCSP request again. Yeah? But in our last class, we learned that we investigated two major open source based web server software, which is Apache and Nginx, and none of them at the time were fully reliable. Right. The last piece of the stakeholder is browser. So browser has to understand what the certificate looks like to mandate the OCSP stable response by looking at the by looking at the certificate extension field, right? So they have to reject the TLS connection if the OCSP response is not stapled by the web server when they receive a certificate with most stable extensions on. Okay, but the bright side was there are only few players that need to take an action to make it possible for web server administrators to begin enabling most stable, because from the individual web server administrators, they don't need to change or they don't need to patch, they don't need to work on something to improve their system because they're relying on web server software. So if major web server softwares patches this, for example, they correctly implement the software, then from the individual web server administrator's perspective, their load is not that huge. Okay, it will be handled automatically. So now, before jumping on I'm going to show you some research, some pieces of research work. But before that, because HTTPS is so important these days, one of the mostly widely used these days, so there are many extensions to add another security layer on top of HTTPS. So let me just introduce based on the keyword, right? And I'll briefly talk to you how it works. So if you are more interested in, please take a look. Please use other resources, right? The first one is HTTP strict transport security. Okay, so it is when you go to the web page, for example, using just HTTP protocol, and the website may start to support only HTTPS, right? In that case, the website, the web server tells the client that, hey, please connect through 443. And also, you don't need to connect me to HTTP again because I'm only supporting HTTPS. So when the HTTP response first comes from the web server, it has the response. In the response, there is a header which is called strict transportable security, which lets the client to cache that information for a certain amount of time, so that the client browser perspective, whenever user try to connect the web server using HTTP, they automatically upgrade the connections to HTTPS. Okay. And the next one is HSTS preloaded list. So the one security challenge of HSTS protocol is at the bootstrap phase, let's say a client visits a website for the first time, right? Then it means this is still vulnerability window, so that the man-in-the-middle attacker can catch the HSTS response coming from the web server, so that to force the client to connect the web server only using HTTP. So it is only vulnerable for the website that the client never visited before, right? So it is called a vulnerabilities. It only happens at the bootstrap phase. Okay. So to solve this limitation, so to solve this challenge, HSTS preloaded list was designed mainly from the browser's perspective. So how it works is really simple. As you can tell from its naming, preloaded list, it is a static list managed by browser, so that the browsers can get the answer, so if a web server would like to put their domain name in the preloaded list, then they contact the browser team and ask them to put their domain name in the preloaded list, so that the browser, whenever users type the domain name in their browsers, and the browser first checks whether the domain name is in the preloaded list, and if it is in, then it automatically upgraded to HTTPS. Okay. Another one is HPKP. So as we learned from the motivation slide of the TLS, there could be a man-in-the-middle attacker who tries to steal the connections and to break one connection into two separate connections, and try to make the client believe that it communicates with the original server by returning some the certificate signed by attacker's private key. Okay, of course, the assumption of this, to make this attack happen, the attackers has to make the victim, the client, to store their root certificate, their self-signed certificate in advance, so that to make the client believe the certificate signed by attackers legitimate. Okay, so HPKP was designed to solve this issue. As you can tell from its naming, it is public key pinning. Okay, so the web servers can return the public key information to the client to make the client cache the public key information for a certain amount of time. So if a client sees they check the certificate, even if the certificate looks valid, but the certificate's public key is different from what they have cached before, then the client can reject the certificate. But unfortunately, this protocol has been deprecated because there was some incidents like public key was pinned, but the web server, they forgot they actually pinned their keys, but they just switched their keys, right? So in that case, no one has compromised any private public key pairs, but it was a simple mistake done by a web server administrator, simply changing the key. But still, the client who cached the old keys, they cached their public key information, pinned their public key information, so they started to reject all the other valid keys, right? This accident is called public HPKP suicide. So if you're interested in, please take a look at some articles. There are lots of fun incidents happened before. Another one is called SNI, server name indication. So it is so important protocol. So you use these protocols every day. So I'm not sure how many of you are familiar with the virtual hosting. So the virtual hosting means usually back in the day, back in the old days, each single IP address web server, they host just the one domain name, right? But these days, one IP address, one machine can serve many different domain name, right? This is called virtual hosting, and it can be applied to the HTTPS as well. So let's say one web server manages a different domain name with the different certificates, right? But HTTPS is based on TLS, and the TLS does not care about domain name. TLS is just positioned at the transport layer, so it does not care about the domain name. So what happened was client connects to one server using IP address, and the web server has to know what certificate has to return to the client, right? But because when one web server manages a different certificate without having the domain name information handed by client, the web server doesn't know what certificate to return. Okay, that's the main challenge. So to solve this limitation, SNI this was proposed. So during the TLS handshake process, client can say that, hey, this is the domain name that I'd like to visit. So please return the certificate, match it with this domain name, okay? So SNI can cause some privacy concern because when you look at the SNI field, it is the only field that reveals all the domain name information. So maybe some man-in-the-middle attackers, passive eavesdropper, passive attackers, by looking at the TLS connection and by looking at the SNI information, they know what websites the client would like to visit, right? So of course, there are many efforts to improve the privacy. So recently the protocol called ESNI was proposed, and also TLS 1.3, they encrypt everything, okay? The last one is certificate transparency. The purpose of certificate transparency is it is a public repository. Mainly, it was driven by Google. So whenever a CA tries to issue a certificate, it has to push this information to the repository, okay? Public repository, so that anyone can know, oh, this certificate for this domain name just has been issued, okay? So once the certificate is registered with the CITILOS gives a kind of proof to the certificate, so that the final certificate has to include a proof. Okay, so the browser can check if the proof does exist or not in the certificate. So if it is not, some browser just reject the certificate. For example, Chromium browsers. Okay, so let's go back to the original, the first slide when we discussed in our first class of TLS. So in the case, we all know that website has to get the certificate from the CA, and so that the browser can check the certificate, and by creating a chain of trust, right, and also do some revocation check, right? But here, when the browser gets the certificate from the website, there is a fundamental assumptions in HTTPS. So they participate in TLS and the shake. Once it's done, this authentication fundamentally assumes only the website, the holder, for example, Bank of America or 농협.com, knows this private key. This is so straightforward, because if everyone knows about this private key, it means the other attackers, all the attackers can impersonate this website, right? And also, as we learned from the public key introduction of the public key infrastructure, the fundamental assumption is private key, even though public key is widely disseminated, private key has to be kept in secret at all cost. Okay, because once it's stolen, it means anyone can impersonate you. It is basically similar to your signature. If your signature on your, for example, apartment rent contract, right? If your signature is too simple, basically it means anyone can impersonate you, right? So your too simple signature will loses the authenticity. Okay. So authentication here fundamentally assumes that only Bank of America knows private key, right? But the thing is that today in today's PKI ecosystem, because it is now so complex, there are all many stakeholders. This assumption that I just mentioned is so rare. Okay, so typically when you go to some popular website, the popular website is typically use a CDN, content delivery network, right? So the content delivery network can serve the content to the client on behalf of the origin website, right? The thing is, there are many web servers, domains that relies on the CDNs, right? So what I mean by this third party, when I mean by third party hosting providers, it could be CDN, content delivery networks, or web hosting services, GoDaddy, right? Or cloud providers, right? Like Amazon EC2 machines, okay? Of course, each of them has a different level of involvement. But one thing, for sure is they are all trusted to deliver the content on behalf of the origin, right? So when you take a step back and look at the bigger picture, what happened right now is when you go to the website and you believe that you make a TLS handshake, the certificate comes from a third party hosting providers, and you participate in TLS handshake with the third party hosting providers, and which means if it is done, it means this third party hosting providers knows private key. Okay, not only for the single key, many private keys. So, in other words, third-party hosting providers know their customers' private key, which breaks the fundamental assumption of the TLS handshake, right? So this is one quick example of key sharing. So this domain name was actually captured a few years back, and this domain name is a really popular restaurant, the fast food restaurant in the United States. So when you look at this certificate, you will see in the subject to alternative names, you see a lot of many different domain names in the same certificate, which means this same key is shared across many different domain names. So for example, largest Saudi Arabian ISP and the Secretary of State of government or some banks. So, and what's the problem of this key sharing, right? So basically the first one is it complicates the trust model. Users don't know who they're really trusting. Actually, this research work was done about 5 years ago, and this problem hasn't been solved yet. So the thing is, let's say when you go to some banking website, and even if you believe your content is being served by the domain name you just visited, but most of the time, you will see that this content is actually coming from the CDNs, right? Then when you think about some trust model, actually you trust the banking website you already trust, and you don't trust CDN. Maybe you don't know anything about the CDN companies, right? But in that case, the trust relationship has just been made between you and CDNs, right? So it can create a potential to create a centralization of trust, so as well as single point of failure. So if these third-party hosting providers got compromised and they experience some outage, then you're done. All right, you cannot use any services of this website. Okay? So there can be some research questions. For example, all right, the key sharing is, I know that the challenge, the problem of the key sharing, then is it really prevalent? You might be wondering. And also, what is the potential vulnerabilities and how can you improve it? So let's just look at all the certificate by using a similar approach that we did for the DNS study, right? So for the DNS SEC study, we scanned entire domain name under .com, .org, .net, right? But for this study, we go to each single IP addresses and try to make the TLS connection to port 443 and to get the certificate. Okay. So after collecting all the certificate, we started to analyze, right? And the first key question is, how prevalent of key sharing, right? So x-axis is the number of third-party hosting provider use, and the y is the cumulative distribution function. So as you can tell, only 23% of the website or the certificates is not shared with anyone else, all right? But the others, 76%, they share at least a single key with others, which means it is really prevalent, okay? And when you, and the next question is if this key sharing phenomena is done by popular website or it is just, some small number of unpopular website, right? The x-axis is the Alexa site rank. For those of you who are not familiar with what Alexa is Alexa basically measures the popularity of the website. And there are many different platforms to collect all the website popularity information, such as Tranquil List or Umbrella, Cisco Umbrella List, and others. Okay. So y-axis is fraction of domains hosted on third-party hosting providers. Right. So you can see a nice, interesting, non-linear relationship. So when you first focus on a very top popular website on the top 10K, you can tell 43% of them share at least one key, right? But the thing is, it drops significantly as it beyonds the top K, and it increases gradually. So from the very least popular website, they also use the third-party hosting providers a lot, right? This interesting observation is because we believe for the most popular website, clearly they have an incentive to use, for example, CDNs to serve their contents to global users, right? And for the least popular website, they just do not need to manage not need to purchase physical servers, and they don't need to manage it by their own. So what they decided to do was relying on the third party for example, EC2 machine without owning the actual physical machines, without managing it by themselves, right? So we believe this key sharing is common across the internet, and the economic incentives is the major forces to drive key sharing. And if you take a step back, because we learned that many websites use the third-party hosting providers, so you can think about it as the economic artifact factor, right? So x-axis shows the number of hosting providers compromised, right? So for example, in other words, we would like to answer how many third-party hosting providers you need to compromise to get X percentage of the private keys, okay? If you focus on just the top 1,000 popular website, you just need to compromise a single provider to get the 60% of their private keys. If you're interested in just all website and 10 providers enough to get the 40% of the all sites private key, right? which means now back in the early 2000 and early 2000, at the time the attack vector was mainly the CAs, right? But now we are using cloud services every day, so now the popular hosting services are the prime target for attacks. So here's a quick summary. So due to economy and incentives, the key sharing is prevalent in today's web. So 76% of the keys are shared with someone else. And if we are focusing on just top 10K web page, and then 43% of now they share the private keys, right? So for example, compromising a single hosting provider could put 60% of top 1K web page in danger. So this was the first piece of the work that shows the interesting perspective of TLS. So because the main quick takeaway of this research work is because of the economy incentive and for incentive economy model, sometimes most of the time, the key fundamental assumption of TLS can be broken, right, due to economic perspective. And I'm going to show you another research work which share the same thing, okay? Which is the invalid certificate. So let me skip it. So most of the studies done so far, we focus on valid certificate, right? Because if the certificate is invalid, then it is so obvious that the client would reject the certificate. So we believe that back in 2016 or 2017, we believe that the majority of the certificates out there in the ecosystem are valid, right? So to answer this question, right, we first get all the certificate by using IPv4 scan, which is the same source of the data set that we use, right? And we validate it, right, by creating a chain of trust, and we validate it, okay? Then shockingly, the conclusion was 88% of the certificates were actually invalid, okay? Which means either they have a broken signature, or it is signed by it is just a self-signed certificate. So at the time, 88% of the certificates were invalid, right? Which is the vast majority, okay? Then you might be wondering, why are these certificates, the majority of them is invalid? Because it would be rejected by the client anyway, right? So I'm going to show you some interesting perspective of these invalid certificates, right? The first question is then, who is advertising this invalid certificate? Who is serving this invalid certificate? And the second one is, what's the differences of such invalid certificates? And third one is kind of application using this invalid certificates, right? So for valid certificates, when you focus on the issuer field, as we learned from the first class of the TLS, you can check who issues the certificate by looking at the issuer field, okay? In case of valid certificate, it is all the CAs are valid, right? Because it is so obvious. So for example, GoDaddy, Rapid SSL, or GeoTrust. But in case of invalid certificate, you will see some random names, right? Long-term systems and localhost, or sometimes it is just empty. The common name is just empty, or some the networks attached storages, NAS, right? Or just virtual machine. So invalid certificates are largely issued by the very hosts who serve them. So in case of a local system, it is the VoIP phone, voice over IP. So they share the same certificate, actually, same invalid certificates. The serial number is different, but they share the exactly same public key, which means if one is stolen, then all the other communication will be vulnerable simultaneously. Yeah. So, and also, we can, so each network has its AS type, right? For example, if you're using SK Telecom, LG Telecom, then most of the ISPs that you're using in home is for residential purpose, right? In the case, right, or this in case of Facebook data center, right, it is for the enterprise. Or if the IP address is managed by CDN, then it is for content delivery network. So what I would like to say is, by looking at the IP address, we can conjecture what kinds of ASs are serving this certificate. Okay. So in case of valid certificate, it is from the transit access, like normal ISP, residential ISPs, and the majority of them are also from the content delivery network, right? But when you see this kind of invalid certificates, the majority are from at the residential transit access, right? It is because IoT devices and lots of just residential devices. So I'm going to deep dive into this phenomenon later. So most invalid certificates are hosted on a major ISP. Okay? So, and also when you look at the IP addresses and their ISPs, then invalid certificates are actually mainly from the residential ISP. Korea Telecom, right? KT. Telefonica Germany is the famous, popular German ISPs, and Comcast, the largest ISP in the United States, and Deutsche Telekom in Germany. Okay. So then what's the differences? So when you look at the first perspective is expiration date. So as I mentioned at the second class, TLS certificate has a validity period. So in case of valid certificate, most of them is just 1 year at the time. But in case of invalid certificate, it doesn't care, right? It can go beyond 20 years or 1 million years, okay? Like 3,000 years, okay? Because they don't care, right? Because it is already invalid, so who cares, right? It is so obvious. So expiration date is 10 or 1,000 times longer. And interestingly, then one may expect that the reason why they specify this so long period of validity period is they may want to use this certificate much longer time. But in reality, when you look at this certificate advertisement period, right, then what you will see is most of the certificates, 60% of the certificate only appear at just the one single day, which means most of 60% of certificate just to use at a single day, and you will not be able to see the same certificate ever again, right? This is so bizarre because this certificate's validity period is really long, like 20 years, which means you can actually use the same certificate for 20 years. But when you scan the internet, the certificate that you see today, 6% of them, you cannot see ever again, right? This is so weird, right? And also when you see their key sharing phenomena, and invalid certificates are really pervasive. So one certificate, one public key can be used for many, many, many different certificates, right? So let's take a look why is it happening. So before that, let me quickly summarize. Comparing to valid certificate, invalid certificates has a long expiration date, but a shorter lifetime. And the key sharing is very prevalent, and also it is mainly used by end user home ISP. So let's take a look. So the thing is, what you found before moving on to application part, the reason was, as you can tell from the last bullet, it is because of home users. It is because the devices was located in the home ISP. So this is what I'm going to talk about is also handled in computer networks class 101, right? So when you, so in your home, your IP address assigned by your ISP, okay? Typically, you're using dynamic IP address every day, which means you do not use a static IP address, and your IP address today probably will be different from the IP address you will use tomorrow, which means it is using a DHCP protocol, right? So ISP, if they have, for example, 3,000 customers, then the ISP do not need to own 3,000 different IP addresses, because sometimes the users just do not connect to the online, do not use do not use the internet. So at the time, the ISP can do not need to allocate IP address to the customers, right? So typically, the number of customers is much larger than the number of the actual IP addresses managed by ISP, right? Because of that, ISP typically change the IP addresses that are assigned to the customers every day or every certain hours, basically on a regular basis, right? So if you'd like to, so for example, let's say your router uses most of these days, each router, most of the routers has a dashboard so that even if you're in the outside of the network, you can connect to the web server managed by the routers to see the configuration file. To encrypt the channel, the router uses a HTTPS certificate. But back in the days, HTTPS certificate was really expensive, so you have to pay CAs to get the certificate. So what they decided was to generate the self-signed certificate, right? And also routers do not have the domain name, so what they decided was generate a certificate, but using the IP address, okay? And self-signed certificate, and the common name is IP address, and also ISP changes IP address every day. So routers basically they need to issue a same certificate a different certificate every day whenever IP address changes, right? And also maybe in this process, some routers decided to use the same public key every day, but a certificate is different, right? So that was the reason why public key sharing is pervasive when it compares to the public certificate, right? So using all these features, actually we can use this property to play around with English certificate. So as I mentioned before, same public key can be used for many different certificates. So if you think a kind of privacy perspective, let's say your IoT devices at your home, it issues a invalid certificate every day, but keeping the same public key, but from a different IP address, right? Then what attackers can do is it basically scan entire IPv4 spaces, and whenever it sees the certificate with the same public key every day, it can track your behavior. Okay, so let's say you bring your own IoT devices at your home. Let's say you move it to, for example, somewhere else, right? And the next day, your device, by using the same public key, but generate a new certificate from a different IP address. So what I can tell is, broadly the attacker's perspective, it can link this two certificate from two different IP address, but share this because they share the same public key, so that they can link it together. And using the IP address, they can estimate your location, okay? So you can actually do so by scanning all the invalid all the certificates by scanning IPv4, and I'm going to skip it. So this tells you how we can group all the different certificates together, okay? But let me skip it. So we can evaluate this link to certificate by using the IP address, but also let me skip it. So in this example, we found that one router, Wi-Fi router, they share the same IP, they share the same public key every day, and also they issue the same certificate, the different certificates every day, but sharing the same public key, so that we can link it together. So of course, as I mentioned before, this one application would be tracking end user devices. So let's say we can group multiple certificates together, but this certificate changes, IP address changes over time. Then we can track users' device movement, right? So typically, whenever physical movement happens to another geographic location, the IP address changes so that we can estimate the location. So we found that, for example, 10K devices moved out the US, and 1 million certificates from the Playbook. It is a small Android devices that was really popular about a few years back because they used their certificate issuer name was just the MAC address, which does not change because the MAC address is bound to its device. And also using this approach, we can infer ISP's IP assignment policy. Basically, we can tell whether this ISP changes IP addresses every day or every 6 hours or using a static IP address. Okay. So what we found was, interestingly, 2K ASs, they use a static IP address, right? Or 15 ASs assign new IP address every day, basically, like this. So typically, yeah. So the conclusion is invalid certificate constitute the vast majority of the certificates on the internet. And one thing I'd like to add is this study was done about 6 years ago. At the time, getting a certificate is requires some fees. Okay, but now these days, this process, getting a certificate, is free using Let's Encrypt. If you're not familiar with the Let's Encrypt, you can take a look at the online. You just Google it. Let's Encrypt is free and automated CA to allow you to get the certificate for free and in an automated fashion. Okay, so now these days, many IoT devices started to use Let's Encrypt certificate. So I believe the percentage of invalid certificate should be dropped significantly. Yeah. But again, the quick takeaway is, similar to the previous topic, the TLS protocol itself, if you're using a valid certificate from the CA, this model is really great. It gives you a guarantee of authenticity and integrity. But when the economic factor is not involved in this design process, right? So but the economic factor has to be involved in whenever you're using the actual protocol in your life, in your real life, right? So because of that, sometimes the protocols work in a way which never intended. Okay, so that is the reason why just inventing a protocol and also deploying a protocol and managing a protocol, it has to be all come together and research together to improve a certain protocol. Okay, so invalid certificate can be linked using a kind of latent features, and can provide a valuable insight into the certificate ecosystem, such as IP address change policy or end user devices, tracking end user devices. Okay. So if you want to test all these analysis and if you want to interpret the data on your way, you can go to this website and get the data set and just start it to analyze and just make some fun things, right, using data set. So let me briefly recap today's the lesson. So HTTPS, because of the economic factors, some certificates can be used, the same public key pairs can be used by shared by many different domain names, which means 1/3 hosting provider can use the same single key to serve many domain names, which becomes a kind of fundamental single point of failure. And Let me show you one example. So let's say, oops. Let's say I just go to google.com and let's say I'd like to see the content, right? Details and extensions. There is a, hold on. Where is it? Subject to alternative names. Here you go. Oh, there is only google.com. It's weird. Okay, this should not be the best case example. Let me see. Hold on. Okay. So I couldn't find a good example. I thought that the yeah, in that case, YouTube certificate, when you look at the YouTube certificate, you'll see a bunch of different domain names here. But in that case, it doesn't, it is nothing wrong with it because all these domain names listed here are actually managed by Google, right? Android.com, Google.com, Google Analytics, right? But sometimes when you go to the website served by CDNs, sometimes they put the different domain names managed by a different entity in one certificate, which means the certificate and the public is shared by many, many entities, right? Which is potentially, problematic. So this was the quick takeaway of this research work. And invalid certificate is because of the certificate is costly, right? At the time, so many people decided to use the invalid certificate, basically self-sign the certificate, right? And because most of the end user IoT devices does not have a domain name, so they use a common name, IP address as a common name, and also IP addresses changes every day. So they started to reissue a certificate whenever their IP address changes, right? Which make the entire invalid certificates number inflated, right? 88%, right? So yeah. But now again, I believe this invalid certificates percentage drops significantly thanks to many automated and free CAs like Lesson Curve. So if you like to use some, if you like to open your website, right, and hosting your domain by yourself, try to serve the content using HTTPS, then I'm sure that you typically should be familiar with Lesson Curve Certbot. Okay. All right, this is it. And again, if you have any questions about TLS or any kinds of research work related to TLS, feel free to send me an email, tj@vt.edu. All right. Thank you so much, and see you at the next class. Bye.